Hi folks, welcome back. I hope you're all doing well. The paper I'm looking at today is not so much a research paper as it is a manifesto, as it says in the title. And what drew me to it is that it talks about a very important trade-off that almost every paper on static analysis makes. And of course, also the title is really catchy because it's a play on the word truthiness. Static analysis is a very active area of research in computer science and also extremely useful in practice. It is used for things like refactoring support, detecting bugs, detecting security vulnerabilities, and many other things. And there is a fundamental trade-off between the soundness of any static analysis and its precision and how scalable it is. What do we mean by those terms? Soundness is the property that the static analysis models all possible execution paths in the program that it is analyzing. And what this usually means is that the analysis is conservative. It computes an over-approximation. It will model behaviors and execution paths that actually may never happen at runtime. The precision of an analysis is how much you can avoid that conservative over-approximation. And scalability is the ability for a static analysis algorithm to work on very large code bases. So obviously, you want your analysis to be sound. You also want it to be precise, and you want it to scale to large code bases. But you cannot have all three. There's an inherent trade-off here. And the trade-off comes when you try to model complex language features in a sound manner. And what usually happens when you try to do that is that your analysis either becomes so imprecise that it's useless, or it cannot scale to large code bases. Let's take some concrete examples. If you look at C or C++, they have this feature set jump and long jump, which lets you change control flow in very arbitrary and dynamic ways. Of course, in C and C++, you also have the ability to do a lot of essentially arbitrary pointer arithmetic. And because these features are so freeform, static analysis has a very hard time modeling these accurately. In languages with virtual machine runtimes like Java and C#, the two features that trip up static analyses are reflection and integrating with native code. The problem with native code is that you cannot make any guarantees about what that native code is doing to the state of your program. And the problem with reflection is that it's highly dynamic. You can't tell at compile time just by looking at the code what execution effect code that uses reflection is going to have. And then if you look at dynamic languages, the authors mentioned JavaScript here, but this is true also of languages like Python and Ruby. You can do things like eval a string that's constructed at runtime or load code dynamically. And again, static analysis is going to be pretty much at a loss when trying to model these features. What most static analyses do is that they have a sound core for tractable and well understood language features, basic things like control flow, data flows, and so on. And the analysis does a good job of soundly modeling them. But then you have some of these very dynamic and freeform language features, like the ones we just looked at, that most static analyses will under-approximate. In other words, rather than assume, for example, that eval can change the state of the entire program because it is possible for eval to do that, a practical static analysis will simply assume that eval does nothing. So that is an under-approximation, and that would make the analysis unsound. And the authors coined the term soundy for an analysis which makes this trade-off in that it is conservative with most language features, but under approximates these highly corner case intractable language features like eval or set jump long jump. If you look at most of the published static analysis papers out there, they are not sound but actually soundy, which is not to say that these soundy static analyses are not useful. They are still useful even though they've given up some amount of soundness. For use cases like autocomplete in IDEs or code navigation or refactoring or just bug detectors which point you to the possibility of bugs, such static analyses are quite useful. What the authors really are calling for over here is to more precisely characterize the degree of soundiness, so to speak, of these static analysis algorithms. For example, if you are being unsound in how you model eval, which is fine because that's what's going to make your static analysis practical, we also need to have some idea of how common eval is in large code bases and how it's used. In other words, we need to understand the implication of the unsoundness being introduced when we under-approximate these complex language features. So that's the central trade-off that the authors here are pushing the research community to make explicit and to try and quantify in some way. I hope you enjoyed that, and I will see you next time. Thank you very much.